every fire in every star, every spark in your brain, every atom in your body may be connected by a secret so strange it sounds impossible. There may not be trillions upon trillions of electrons in the universe. There may be only one particle, one electron, a single tiny object moving back and forth through time, creating the illusion that every electron in existence is separate. This was not science fiction. This was a real idea proposed by one of the greatest physicists who ever lived, and it may completely change how you see reality. Tonight, we are stepping into one of the strangest concepts in modern physics, a theory so bizarre that it sounds like fantasy, yet it came from the mind of John Archibald Wheeler, the legendary physicist who helped shape black hole theory, quantum gravity, and the very language of space-time itself. His claim was simple. Every electron in the entire universe is the same electron, not similar, not copies, the same one. It is one of the boldest scientific ideas ever spoken. And even though modern physics does not accept it as literal truth, this thought experiment opened doors that changed physics forever. By the end of this video, you will on. They understand why electrons are so mysteriously identical. Why this baffled the world's greatest scientists, how Richard Feynman used this idea to help reshape particle physics, and why the answer may be even stranger than Wheeler first believed. Because hidden inside this mystery is a terrifying possibility. Reality may not be made of separate things at all. To understand why this idea shook physics, we need to start with something so ordinary that most people never question it. The electron. It is everywhere. Electrons flow through wires to power cities. They dance through your nervous system to create thought. They bind atoms together to form molecules, water, DNA, planets, and people. Without electrons, matter as we know it would collapse. They are among the most important building blocks in existence. And yet, almost nobody talks about one deeply unsettling fact. Every electron in the universe is exactly the same. Not mostly the same. Not nearly identical. Perfectly identical. Every single electron ever observed has precisely the same mass, the same electric charge, the same spin, no defects, no variation, no hidden uniqueness. An electron inside your brain is indistinguishable from one inside a distant galaxy billions of light years away. An electron formed near the birth of the universe behaves exactly like one created yesterday in a particle accelerator. This is not normal. In fact, it is deeply weird. Look around at the no two snowflakes are perfectly alike, no two fingerprints match exactly. Even identical twins are not truly identical down to every detail. Nature usually produces variation, tiny imperfections, differences, but electrons break that pattern completely. They are flawless copies with no detectable individuality. This raises a profound question. Why? Why does nature produce a particle with such absolute sameness? Why should every electron everywhere across all of cosmic history be exactly indistinguishable? This was not a small technical detail. For physicists, it became a profound philosophical problem. Because if particles are truly fundamental, you might expect each one to possess some tiny signature, some microscopic identity, some unique label. But electrons do not. It is as if nature mass produces them from a single perfect blueprint. Or perhaps something even stranger is happening. This mystery struck John Wheat. Lure with extraordinary force. Wheeler was not an ordinary thinker. He was known for pushing physics into radical territory. He helped popularize the term black hole. He explored wormholes, quantum foam, and the architecture of space-time itself. He was willing to ask questions others were afraid to touch. And one day, he asked a question so radical it sounded absurd. Why are all electrons identical? His answer was even more shocking, because they are all the same electron. According to Wheeler's proposal, there are not countless separate electrons scattered across the universe. Instead, one electron traces an unimaginably complex path through space-time. It moves forward in time, then backward, then forward again and again, crossing the universe in loops so vast and chaotic that from our limited perspective, we perceive many electrons. But in truth, it could all be one particle appearing in countless places across time, a single actor playing every role. This idea was so strange that even today it sounds like a cosmic riddle. But Wheeler was serious, and his student, Richard Feynman, would take part of this bizarre concept and transform it into something revolutionary. Because when an electron moves backward through time, something astonishing happens. To us, it may appear as antimatter, a positron, an anti-electron. Suddenly, Wheeler's wild speculation touched one of physics' deepest discoveries. Matter and antimatter may be linked in ways that challenge ordinary logic. This is where the story stops being merely weird and starts becoming scientifically powerful. Because even though the one electron universe is not considered physically correct, pieces of its logic helped shape the mathematics of quantum electrodynamics, one of the most accurate scientific theories ever created. In other words, an idea that sounded insane helped unlock real truths. And that is where this journey becomes truly fascinating. Science is not just a collection of facts. Sometimes progress begins with outrageous questions. Questions that seem impossible. Questions that force reality to reveal deeper layers. The one electron idea is one of those questions. It forces us to confront a disturbing possibility. At the deepest level, individuality may be an illusion. The universe may not care about separate identity the way humans do. Particles may not be tiny, unique objects. Objects, they may be a field, a pattern, a repetition. This is one of the reasons modern physics feels so unsettling. The deeper we look, the less reality resembles common sense. And this is only the beginning, because to truly understand whether one electron could explain the universe, we need to go deeper into space-time itself, into the strange birth of antimatter, and into the mathematical revelations that change physics forever. By the end, you may never look at your own body or the atoms around you the same way again. Because every breath you take depends on electrons. And those electrons may hold one of the strangest secrets in existence. Welcome to the channel. If you are drawn to the deepest mysteries of space, physics, and reality itself, subscribe now and join us as we explore the universe far beyond the obvious. In 1940, long before black holes became household words, long before quantum theory reached its modern form, a conversation took place that sounded less like science and more like a crack in reality itself. John Wheeler picked up the phone and called Richard Feynman. At the time, Feynman was young, brilliant, and already developed, opening the sharp intuition that would later reshape physics. Wheeler was his mentor, but he was also something more dangerous. He was fearless. He was willing to chase ideas far beyond accepted boundaries. And during that conversation, Wheeler delivered a statement so bizarre that it would echo through physics for decades. Why are all electrons the same? Then came his answer. Because they are all the same electron, not metaphorically, not symbolically, literally. According to Wheeler, every electron that had ever existed might actually be one single electron moving in an enormous tangled path through space-time. This was not just an unusual guess. It was a radical assault on the basic idea of individuality in physics. To understand how strange this was, it helps to remember the era. In 1940, physics was in a transitional state. Quantum mechanics existed, but many of its deeper structures were still unclear. Quantum field theory, the framework that now explains particles as excitations of universal fields, had not yet fully matured. Scientists understood electrons as real particles, but the true nature of their sameness remained deeply mysterious. Why should electrons be perfect? Duplicates? Why should everyone carry exactly the same charge, the same mass, the same spin, with no variation across the universe? Wheeler did not accept this as a boring coincidence. He suspected something deeper. His proposal was staggering in its simplicity. Suppose the countless electrons scattered across the cosmos were not countless at all. Suppose there was only one electron. This single electron would move through time the way a thread weaves through fabric, forward, backward, looping, crossing its own path over and over again. Each segment of that path from our limited perspective would appear as a different electron existing in a different place. In this view, the universe was not filled with endless particles. It was filled with one particle tracing an unimaginably vast pattern, a hidden cosmic line stretching across all history. This was not merely strange, it was revolutionary. Wheeler was effectively suggesting that time itself could create multiplicity. Many could be one. Separate could be illusion. This concept was so extreme that even by the wild standards of theoretical physics, it stood apart. And yet, Wheeler was not proposing nonsense. He was trying to solve a genuine puzzle: particle identity. Why perfect sameness exists at all. His idea also contained a strange hidden power. If an electron moving one direction through time appears normal, then an electron moving backward through time might appear as something else entirely, something opposite. This detail would become explosive because nature had recently begun revealing evidence of antimatter. Wheeler's thought was not polished mathematics. It was more like conceptual dynamite, a bold leap before the equations fully existed. And this is why the call mattered. It was one of those rare moments when physics stopped asking how the universe behaves and started asking whether reality itself had been misunderstood from the beginning. To grasp Wheeler's idea, space alone is not enough. Everything changes when time becomes part of the map. In everyday life, people think of movement as traveling from one place to another. A car moves down a road. A planet circles a star. A bullet crosses a room. But modern physics sees something deeper. Every object does not simply move through space. It moves through space-time. This was one of Einstein's greatest revolutions. Space and time are woven, and together into one four-dimensional structure. Every particle traces a path through this structure from past to future. Physicists call this path a world line. A world line is like the full story of a particle's existence, not just where it is, but when it is. Your body has one, every atom has one, every electron has one too. Normally, a particle's world line moves steadily forward through time, second by second, because before effect. This is how reality seems to work. But Wheeler asked a forbidden question. Who says the path must always move only one way? His proposal suggested that a single electron's world line might twist and loop through space-time in ways far stranger than common sense allows. Instead of moving from past to future in one clean line, this electron could reverse direction. Forward, backward, forward again, over and over. From the outside, each section of this giant looping thread could appear to be a completely separate electron. A particle here, another there, billions everywhere. But beneath the illusion, all of them could be one entity crossing time repeatedly. This was the real shock. Multiplicity might simply be one object intersecting history from different angles, the same traveler appearing again and again across cosmic time. This sounds impossible, but physics was already beginning to reveal clues that made it less absurd than it first seemed. In 1928, Paul Dirac developed an equation combining quantum mechanics with Einstein's relativity. It described the electron with astonishing accuracy, but buried inside the math was something deeply disturbing. The equation allowed solutions with negative energy. At first, this looked like nonsense. Then came a terrifying possibility. These strange solutions might represent a real particle, a mirror version of the electron, same mass, opposite charge, antimatter. In 1932, Carl Anderson discovered the positron in cosmic ray experiments, confirming that antimatter was real. This changed everything. Suddenly, Wheeler's looping electron gained a bizarre new layer. If an electron moved backward through time, it would mathematically resemble a positron moving forward through time. This was not just philosophy. In certain equations, it worked. A positron could be interpreted as an electron traveling in reverse through the time dimension. This was one of the strangest insights in all of science, and timitar might not be some completely separate category of existence. It might be ordinary matter moving differently through space-time itself. The implications were staggering. Time direction could define particle identity. Past and future might shape charge. The arrow of time might be more than sequence. It might be part of what creates the universe's apparent diversity. For a moment, reality became deeply unstable. Electrons and positrons were no longer just particles. They became clues, signs that time may behave in ways human intuition was never built to understand. And for Richard Feynman, this strange possibility would become far more than a thought experiment. It would become a mathematical weapon powerful enough to rewrite particle physics itself. By the late 1920s, physics was already standing on unstable ground. Quantum mechanics could explain atoms. Einstein's relativity could explain motion at extreme speeds. But these two pillars did not fit together cleanly. Electrons, the tiny particles shaping matter itself, were trapped between two incompatible worlds. Then Paul Dirac entered the story. Dirac was not known for dramatic speeches or wild speculation. He was quiet, intensely mathematical, almost machine-like in precision. But in 1928, he wrote an equation that would quietly detonate reality. His goal seemed straightforward: describe the electron in a way that obeyed both quantum mechanics and special relativity. What emerged was one of the most beautiful equations in science. It correctly explained electron spin, magnetic behavior, and other strange properties with stunning elegance. But hidden inside that beauty was something deeply unsettling. The equation produced extra solutions, mirror solutions, versions of the electron that should not have existed. These solutions carried the same mass as an electron, but opposite charge. At first, even Dirac hesitated. Negative energy states looked absurd. Some physicists hoped they were just mathematical garbage, but Dirac trusted the math. He proposed that these strange solutions represented a real particle, an anti-electron, a positron. This was one of the boldest predictions in scientific history. And for a few years, it remained only theory. Then in 1932, American physicist Carl Anderson studied cosmic rays using a cloud chamber and magnetic field. He saw something impossible. A particle moved like an electron, but in the wrong direction. Same mass, positive charge. Dirac was right. Antimatter was real. This discovery changed physics forever. Nature was stranger than anyone expected. Every particle might have an opposite. Matter was not unique. Reality had a mirror, but Richard Feynman pushed this even further. Influenced partly by Wheeler's radical thinking, Feynman saw that positrons could be interpreted mathematically in a shocking new way. Instead of treating a positron as an entirely separate object, the equations often worked if you described it as an electron moving backward through time. This was not just a poetic metaphor. It became It became an extraordinarily powerful. Feynman transformed particle interactions into visual mathematical maps, now known as Feynman diagrams. These diagrams look deceptively simple. Lines, arrows, intersections, but they encoded some of the deepest processes in the universe. An electron moving forward, a positron moving backward, particles colliding, annihilating, reappearing. For physicists, these diagrams became revolutionary. They turned impossible calculations into manageable logic, and they helped build quantum electronics. CT rhododynamics, or QED, the theory describing how light and matter interact. QED became one of the most accurate scientific frameworks ever created. Its predictions match experiments to astonishing precision, sometimes to more than 10 decimal places. This is where Wheeler's bizarre philosophical leap mattered. His literal one-electron universe was not accepted as physical truth. There is no evidence that all electrons are one particle weaving through time. But the conceptual boldness behind the idea helped inspire a new way of thinking. Sometimes an outrageous idea is valuable not because it is correct, but because it forces better questions. Wheeler's speculation cracked open a door. Feynman walked through it with mathematics. Dirac provided the foundation. Together, their ideas transformed antimatter from a strange prediction into a usable language of reality itself. And yet, for all this brilliance, a devastating problem remained. If electrons and positrons are so deeply connected, why does the universe seem filled mostly with one and not the other? For a brief moment, Wheeler's idea seemed almost too elegant. One electron, one cosmic thread, one particle weaving through tie. May appearing as both electrons and positrons, depending on direction. It was bold, it was beautiful, and then reality interfered, because the actual universe does not seem balanced at all. Everywhere scientists look, matter dominates. Stars are made of matter. Planets are made of matter. Gas clouds, galaxies, black holes, and human bodies are all built from ordinary matter. More specifically, they are filled with electrons. Positrons, the electrons, antimatter twin do exist, but they are rare. They appear in radioactive decay, lightning storms, high energy collisions, and certain cosmic events. Then they vanish. When a positron meets an electron, both are destroyed in a flash of energy. This process is called annihilation. If Wheeler's one electron concept were literally true in a simple, symmetrical way, the single electron looping backward and forward through time should produce roughly similar numbers of electrons and positrons. The cosmic count should feel more balanced, but it does not. The observable universe appears overwhelmingly biased toward matter. This is not a small detail. It is one of the deepest unsolved problems in physics. Why does anything exist at all? Accord. NG to many models of the early universe, the Big Bang should have created matter and antimatter in nearly equal amounts. If that happened perfectly, most particles would have annihilated each other, leaving behind mostly radiation. No stars, no planets, no people. And yet matter survived. Some tiny imbalance favored matter over antimatter. That imbalance shaped everything. This mystery is called baryon asymmetry, or more broadly, matter-antimatter asymmetry. And it cuts directly into Wheeler's idea. Because if one electron were zigzagging through time, generating both electrons and positrons, where are all the missing positrons? Why is the universe not overflowing with equal counterparts? Wheeler himself recognized this issue. In fact, one lesser-known detail is that he jokingly suggested the missing positrons might somehow be hidden in places humans had not yet observed. Perhaps deep in proton structures, perhaps beyond visible scales, perhaps in ways not yet understood. But these were speculative gestures, not rigorous solutions. As experiments improved, the problem only grew sharper. Particle detectors became more precise. Cosmic observations expanded. The imbalance remained. Even entire antimatter galaxies appear absent from the visible universe. If large antimatter regions existed nearby, scientists would likely detect intense annihilation signatures where matter and antimatter boundaries meet. They do not. This silence matters. It suggests the cosmos itself is structurally uneven, and that unevenness breaks the clean symmetry Wheeler's idea seems to require. This is why most physicists do not treat the one electron universe as literal physical reality. It is brilliant as metaphor, powerful as inspiration, useful as conceptual fuel. But as a complete explanation, it collapses under observation. Nature appears more complicated than one elegant loop. Reality refuses to fit perfectly inside poetic simplicity. Still, this failure does not make the idea worthless. In science, wrong ideas can still reveal hidden truths. Wheeler's concept forced physicists to confront identity, antimatter, and the strange architecture of space-time in radically new ways. And as the literal theory faded, a deeper explanation began to emerge. One that preserved the eerie sameness of electrons without requiring them to all be the same particle at all before antimatter was ejected. ER scene, it was written not in a telescope, not in a laboratory, but in mathematics. In 1928, Paul Dirac was trying to solve one of physics' greatest problems. Quantum mechanics explained the tiny world. Einstein's relativity explained the fast world. But electrons lived in both. No existing equation fully captured that reality. Dirac wanted a deeper formula, one that described the electron moving near light speed while obeying quantum law. He found it, and at first it looked like genius. His equation explained electron spin naturally, something previous theories struggled to do. It matched known experiments with astonishing precision. But then came the impossible part. The math produced two answers. One described the normal electron. The other should not have existed. This second solution had the same mass but opposite charge, a mirror electron. At first, this terrified physicists. Negative energy states seemed absurd. Some thought the equation had failed. Dirac disagreed. He trusted the structure of mathematics more than human intuition. He proposed that this strange solution represented a real particle, not a flaw, not an error, a hidden half of nature. 4 years later, in 1932, Carl Anderson detected the positron in cosmic ray experiments. A particle curved through a magnetic field exactly like an electron, except in reverse. Same mass, positive charge. Dirac's impossible particle was real. This was one of the greatest predictive victories in science. For the first time, mathematics had revealed an entirely new form of matter before nature visibly confirmed it. But Richard Feynman pushed the logic into even stranger territory. Feynman was deeply influenced by Wheeler's radical style of thinking. Wheeler's one-electron universe may not have been literally correct, but it planted a dangerous idea. Maybe particle identity could be reinterpreted through time itself. Feynman realized something extraordinary. In the equations, a positron could often be treated as an electron moving backward through time. This was not science fiction. It was a mathematical shortcut that actually worked. And this insight became part of one of the most powerful tools in theoretical physics, Feynman diagrams. These diagrams changed everything. Instead of drowning in endless equations, physicists could represent particle interactions visually through lines and vertices. An electron moved one direction. A positron could be drawn as the same particle moving the opposite way through time. Particles exchanged photons. Matter and antimatter annihilated. Energy transformed. Complexity became manageable. This was more than symbolism. It allowed scientists to calculate real physical outcomes with astonishing accuracy. Quantum electrodynamics, the theory born from this framework, became one of the most successful scientific achievements ever created. Its predictions match experiments so precisely that some results are accurate to parts per trillion. That level of precision is almost beyond comprehension. This is where the distinction becomes crucial. Wheeler's literal claim that all electrons are one electron is not accepted as physical fact. There is no evidence that a single particle is weaving through all existence. But the deeper conceptual leap that time direction can reshape particle interpretation proved profoundly useful. A wild philosophical idea became mathematical infrastructure. This is one of science's strangest patterns. Sometimes the universe rewards bold wrongness. An idea can fail as literal truth, yet still unlock deeper laws. Dirac ENC. Over antimatter, Wheeler challenged identity. Feynman transformed both into a working language of reality. And yet one devastating contradiction remained. If matter and antimatter are so deeply connected, why does the cosmos itself seem to overwhelmingly choose one side? Wheeler's vision was breathtaking. One electron stretched across time, creating the illusion of many. It was elegant. It was haunting. But modern physics found a different answer. And in some ways, it is even stranger. Today, the leading framework is quantum field theory. This theory does not treat particles as tiny, independent objects bouncing through empty space like microscopic marbles. Instead, it says something far more radical. The universe is filled with fields. Invisible, continuous fields exist everywhere, not in some places, everywhere. There is an electron field spread across the entire cosmos, a photon field, a quark field. Even the vacuum itself is not truly empty. It is a restless sea of fields vibrating with hidden possibility. In this view, an electron is not a standalone thing in the deepest sense. It is a localized excitation of the electron field, a ripple, a disturbance, a quantum vibration. Ion, this is the key. Every electron is identical because every electron emerges from the same underlying field. Not because all electrons are secretly one particle, but because they are all expressions of one universal source. This is similar to waves on an ocean. 1,000 waves can rise in different places. They can crash separately, travel independently, appear distinct, but each wave is made of the same water. In quantum field theory, electrons are like waves in the same cosmic field. This framework explains their perfect sameness with extraordinary power. Every excitation of the electron field must obey the same fundamental rules. Same mass, same charge, same spin. There is no room for random variation because the field itself defines the particle. This solves the identity problem more effectively than Wheeler's looping time hypothesis. It preserves the eerie perfection of electrons without requiring one particle to repeatedly zigzag through space-time. And yet, this does not make reality feel less strange. In fact, it may be even more unsettling, because this means particles may not be fundamental objects at all. Fields are deeper. Particles may simply be temporary appearance, numbers, patterns in something larger. This idea reshaped physics in the 20th century. Quantum electrodynamics, the Standard Model, and much of modern particle science all depend on this field-based understanding. Experiments repeatedly confirm it. Particle accelerators do not just smash little balls together. They excite fields. They pull hidden structures from the vacuum. Some physicists even describe particles as secondary, almost like surface effects of deeper systems. So Wheeler was wrong, but not foolish. His idea was poetic, where quantum field theory became precise. He sensed that identity itself required a more profound explanation. And he was right about that. He simply reached for the wrong mechanism. This happens often in science. Alchemy failed, but helped build chemistry. Ancient stargazers misunderstood planets, but helped create astronomy. Wrong paths can still lead toward truth. Wheeler's one-electron universe forced physicists to confront sameness, time, and particle identity in bold new ways. It challenged assumptions. It inspired reinterpretations. It helped create intellectual momentum. Sometimes a theory's greatest value is not in being correct. It is in the folder, assessing reality to answer harder questions. And even now, modern physics still leaves us with something deeply unsettling. Electrons are not unique individuals. They are interchangeable manifestations of a deeper cosmic field. So while there may not be only one electron, the boundaries between many and one may still be far stranger than ordinary thought can comfortably accept. At first, the one electron idea sounds like a strange scientific curiosity, a clever mistake, a historical footnote, but beneath it lies something far more disturbing. It attacks one of the deepest assumptions humans carry every day, that separate things are truly separate. In ordinary life, identity feels obvious. You are you. A tree is a tree. A star is a star. One object exists here, another exists there. Difference seems fundamental. Individuality feels real. But physics has a habit of dismantling common sense. At the deepest levels of nature, electrons do not carry personal identity the way human minds expect. One electron is not this electron in the familiar sense. Swap two electrons anywhere in the universe, and nothing changes. No hidden tag appears. No cosmic label is lost. The equations remain the same. This is not just a technological limitation. It appears woven into reality itself. Nature may not distinguish between individual electrons at all. That is profoundly unsettling because it suggests that individuality, at least for fundamental particles, may be less like a built-in truth and more like a useful illusion. In quantum mechanics, identical particles are so deeply interchangeable that their behavior shapes the structure of reality. The Pauli exclusion principle, one of the laws preventing matter from collapsing, exists partly because electrons are indistinguishable fermions. Your body, your chair, your planet may depend on a universe where identity works very differently than human intuition suggests. This raises a haunting question. If the building blocks of matter lack individuality, where does individuality actually begin? At atoms, cells, brains, consciousness, or is identity itself an emergent story? Something large systems create from deeper sameness. Wheeler's one-electron concept pushed this tension to its extreme. Not merely similar particles, not merely identical laws, but one recurring existence. One thing wearing countless masks across space-time. Even if physics rejects that literally, the philosophical wound remains. How much of reality's apparent multiplicity is fundamental and how much is perspective? This also touches time itself. Humans experience time as linear, past behind, future ahead, because before, effect. But relativity already shattered the idea of universal time. Quantum theory added further uncertainty. Wheeler's speculation pushed even harder, suggesting that movement through time might shape how existence appears. If identity can blur, perhaps causality is more subtle too. Perhaps reality is not simply a sequence of separate events, but a structure far stranger than everyday awareness can grasp. These ideas can feel almost spiritual, but they emerge from physics, mathematics, and rigorous attempts to understand matter itself. This is one reason science can feel so unsettling. It does not merely answer questions. Sometimes it destabilizes the framework of the questions themselves. And this is where impossible ideas become valuable. Science advances not only through correct answers, but through dangerous questions. Questions that sound absurd. questions that force old assumptions to break. Wheeler's idea may not describe the universe literally, but it did something powerful. It challenged the meaning of sameness. It challenged the meaning of time. It challenged whether many is always truly many. So beneath all the equations, particles, and fields, one haunting possibility still lingers. The universe may be built from countless separate things, or it may be something stranger, a deeper unity, a repeating pattern, one reality unfolding in forms so varied that separation itself becomes the illusion. The idea of a single electron moving through all of space-time is not accepted as reality. Modern physics does not support it. There is no evidence that every electron is one particle looping through time. But the strange beauty of this idea is not in whether it is correct. It is in what it revealed along the way. It forced physicists to confront something deeply unsettling. Why are electrons everywhere so perfectly identical? Why does nature produce copies without variation at the most fundamental level? That question did not disappear when Wheeler's literal theory was set aside. Instead, it pushed science forward. It helped inspire new ways of thinking about antimatter, time, and particle behavior. It influenced how Richard Feynman described interactions. It helped shape the language of quantum electrodynamics. And it pointed toward a deeper truth that modern physics now embraces. Particles are not isolated objects with personal identity. They are expressions of underlying fields, ripples in something more fundamental. The one-electron universe was wrong as a literal claim, but it was powerful as a lens. It showed how far intuition can stretch before it breaks, and how breaking that intuition can still lead to real discovery. Even now, the sameness of electrons remains one of the most mysterious facts in physics. Every electron across every galaxy behaves exactly the same way. No exceptions, no individuality, only perfect uniformity across the entire universe. That level of consistency is not something human experience prepares anyone for, and yet it is built into the fabric of reality itself. So the question lingers, not as a claim, but as a challenge. How deep does this uniformity go? Is nature truly made of many separate things? Or is separation only something the human mind adds to a reality that is far more unified than it appears? Physics continues to push T, toward answers, but every layer that is uncovered seems to raise new questions, new mysteries, new boundaries of understanding. And that is where this story truly lives, not in certainty, but in the edge of knowledge where ideas become strange enough to change everything. Sometimes the most important theories are not the ones that describe reality perfectly. They are the ones that force a new way of seeing it. Before you go, like the video, if you enjoyed this journey into one of the strangest ideas in physics, and subscribe for more deep dives into the mysteries of space, time, and reality itself.